Okay, welcome everybody to this final talk for this session. Our final speaker is Laurent Poinsot, who will talk to us about Hilbertian Frobenius algebras. Laurent, the floor is yours.
Thank you very much. So my talk is about Hilbertian Frobenius algebras, which are probably better known as commutative dagger Frobenius monoids in the finite dimensional situation. As is well known, there is a 1-1 correspondence between these Frobenius monoids structures on a given finite dimensional Hilbert space and its orthogonal basis. And this provides a way to speak about Hilbertian bases in a categorical way. Despite the introduction of commutative dagger Frobenius semigroups, that is, non-unital Frobenius algebras, there is still no such correspondence between bases and algebras in arbitrary dimension. This is precisely the goal of my talk, to present such an analog for arbitrary dimensions. This result, the result I will present, is actually a consequence of the semi-simplicity of some Hilbertian Frobenius algebras, which itself follows from a structure theorem. So, first thing first, let me recall some notion about semi-simplicity. So there are several equivalent characterizations of the Jacobson radical of a commutative algebra. In particular, when the algebra is Banach, it is the intersection of the kernels of the non-zero complex valued homomorphisms of algebras, that is the so-called non-trivial characters. In any case, an algebra is semi-simple when its radical is trivial, and it is called radical when the Jacobson radical is equal to the whole algebra. I won't talk about semi-simplicity of Banach algebras in general, but only for what I called Hilbertian algebras. So such algebras are, roughly speaking, this is not entirely true, but it will suffice for this talk. These algebras are commutative Banach algebras whose underlying space is a Hilbert space. Without telling that explicitly in my talk, every Hilbertian algebra will be assumed commutative. Because of the Riesz representation theorem, the Jacobson radical of a Hilbertian algebra has a somewhat internal description. Indeed, the non-trivial characters of the algebra are in 1-1 correspondence with the group-like elements, and so that the Jacobson radical becomes the orthogonal complement of the set of all group-like elements. Once, as a Hilbert space, the underlying space of a Hilbertian algebra splits into an orthogonal direct sum, as indicated in the last line of the slide. This direct sum will play an important role in this talk. So now, in the context of Hilbertian algebras, the notion of semi-simplicity translates into the equality of the carrier Hilbert space of the algebra and the closure of the linear span of its group-like elements. To close this introductory part, let me say a few words about the terminology. So in this talk, by a Hilbertian Frobenius algebra is meant a commutative dagger Frobenius semigroup in the symmetric monoidal category of Hilbert space, together with the tensor product of Hilbert spaces. In other words, it is a commutative Hilbertian algebra for which the Frobenius compatibility condition has depicted in the slide holds. The content of this second part is the proof, or is some elements of proof of the structure theorem for Hilbertian and Frobenius algebras, from which will be deduced a correspondence between orthogonal bases, some kind of orthogonal bases, and structures of Hilbertian Frobenius algebras in the infinite dimensional situation. So the theorem, as given in this slide, states that in the direct Hilbert space sum, the Jacobson radical, G of A, and its complements are ideal, or both ideals, and actually the Jacobson radical is corresponds to the annihilator of the algebra, and they are also both subcoalgebras. It follows then that both Hilbert spaces are Frobenius, radical for the first one, for the Jacobson radical, and semi-simple for its orthogonal complement. So to prove the theorem, I first explain why the orthogonal complement of the Jacobson radical is a subcoalgebra. Actually, this follows from the fact that in any Hilbertian algebra, the orthogonal complement of an ideal is automatically a subcoalgebra. So the orthogonal complement of the Jacobson radical is a subcoalgebra. The orthogonal complement of the Jacobson radical is also a subalgebra. Here, the Frobenius condition, compatibility condition, play an important role. Indeed, given, say, two different group-like elements, X and Y, it is essentially a consequence of the Frobenius condition that their product belongs to the Jacobson radical. But then this implies that there exists an idempotent element which belongs also to the Jacobson radical. Consequently, it is necessarily equal to zero because there is no idempotent, non-zero idempotent elements in the Jacobson radical of a Banach algebra. And thus, the product of the two distinct group-like elements is also equal to zero. To prove that the orthogonal complement is a subalgebra, that it is closed under multiplication, it remains to check that the square of a group-like belongs to the orthogonal complement. Let us consider an arbitrary element U of the Jacobson radical. Then zero is equal by orthogonality to the complex number given by the inner product in the slide, which can be rewritten as follows. And due to the co-commutativity of the adjoint co-multiplication, it can be written as follows. But then, by definition of the inner product of a tensor product, this gives this number as X is a group-like element. It is non-zero. So this implies that X squared is orthogonal to U. As U was chosen arbitrary, this means that X squared belongs to the orthogonal complement of the Jacobson radical. To go further into the detail of the proof of the structure theorem, we need to use a tool from the theory of Banach algebras, namely the notion of quasi-nilpotent elements, and a tool from the theory of Hilbert spaces, namely that of normal operators. Let me recall this notion. So a member of a Banach algebra is said to be quasi-nilpotent when its spectral radius is equal to zero. In general, the Jacobson radical is only included into the set of all quasi-nilpotent elements, but when the algebra is commutative, both sets coincide. An operator, a bounded operator on a Hilbert space will be said to be quasi-nilpotent operator when it is a quasi-nilpotent element of the C-star algebra of all bounded operators on the Hilbert space. Now let us continue with some notation. Let mu be the multiplication operator associated to an element u of the carrier Hilbert space of an Hilbertian algebra. This means that mu is the image at u of the regular representation of the Hilbertian algebra. The Frobenius condition forces this multiplication operator to be a normal operator, that is, to commute with its own adjoint. As a consequence, the Jacobson radical of a Frobenius algebra is automatically equal to the annihilator of the algebra. That is, it is the kernel of the regular representation of the algebra. So indeed, for any Hilbertian algebra, the regular representation maps the Jacobson radical of the algebra into the set of all quasi-nilpotent operators. Assuming furthermore that the multiplication operator is normal, this implies that it is the zero operator, because the spectral radius of a normal operator coincides with its operator norm. Thus, the element by which one multiplies, u, belongs to the annihilator of the algebra. The annihilator of an algebra is always contained into the Jacobson radical, so the second assertion of the previous proposition is proved. That is, the Jacobson radical is equal to the annihilator of the algebra. Now, the first assertion is obtained by direct inspection, where it is not very interesting to see how we obtain that, but what is of interest is that the Frobenius conditions are needed to prove this fact. So this means that every multiplication operator is a normal operator. So now we are in a position to prove the structure theorem for Hilbertian Frobenius algebras in a few sentences. That the orthogonal complement of the Jacobson radical is an ideal follows from the facts that it is a subalgebra and that the Jacobson radical is equal to the annihilator. Since this orthogonal complement is an ideal, its own orthogonal complement, the Jacobson radical, is automatically a subcoalgebra. This structure theorem governs actually the condition under which a Frobenius algebra is semi-simple. As a direct consequence of the structure theorem, one has the following corollary. It shows in particular, so this is written in the last sentence of the corollary, it shows that every special, that means that the multiplication is a co-isometry or its adjoint is an isometry. The special Frobenius algebras are automatically semi-simple. This provides a positive answer to a question raised by Sanson, Abramsky, and Chrysainen in their paper about non-unital Frobenius algebras in finite dimensions. Let me tell a remark about commutativity. So I said earlier that every Hilbertian algebras in this talk were commutatives because this condition is necessary to get the right structure theorem and the right condition for semi-simplicity. Indeed, if I can exhibit an example of a non-commutative special Hilbertian Frobenius algebra, which is not Jacobson semi-simple. It suffices to consider the space of all square summable functions from x to the complex number with the multiplication as given in the slide. Then this algebra is satisfies all the axioms of a special Hilbertian Frobenius algebra, but it is not non-commutative in general. However, it is not semi-simple. There are many, for instance, there are many nilpotent elements in this algebra. So really, commutativity is important for that matter. So now I go back to the condition for semi-simplicity, and I present the analog result in case where the assumption of finite dimensionality is put. The corollary reduces to the following one. So in the case of finite dimensional Hilbertian Frobenius algebras. In particular, we see that semi-simplicity is equivalent to the existence of a unit. And one recovers a result by Bob Coke and his collaborators that states that every finite dimensional dagger Frobenius monoid, so semigroup with a unit, is semi-simple. Recall from the introduction of this talk that the same guys have proved the remarkable fact that structures of Frobenius algebras with a unit on a finite dimensional space and its orthogonal bases are in 1-1 correspondence, and that this correspondence restricts to a bijection between special Frobenius algebras and orthonormal bases. This is rather similar for arbitrary dimension up to the restriction to bounded above or below orthogonal bases. A set in a Hilbert space is said to be bounded above when there exists a strictly positive upper bound for the norms of the elements of the set. This being said, the analog for arbitrary dimension of the main result from Bob Coke and its collaborators is as follows. Bounded above orthogonal bases of a Hilbert space and structures of semi-simple Hilbertian Frobenius algebras on H or in 1-1 correspondence. This correspondence restricts to a bijection between orthonormal bases and the structures of special Frobenius algebras. So I will give you some very brief elements of the proof of this result. So from a bounded above orthogonal basis X of the Hilbert space H, one associates a multiplication that turns the Hilbert space into a semi-simple Frobenius algebra. That's the multiplication as defined in the slide extends to the tensor product of Hilbert spaces is due to the fact that the basis was chosen bounded above. Conversely, given a semi-simple Frobenius algebra, its group-like elements form a bounded above orthogonal basis. Finally, the operations are both invertible and they are inverse one from the other. So now in the fourth and last part of my talk, I provide several category theoretic observations. So let Frob be the full subcategory of commutative semigroups in the category of Hilbert space spanned by the Frobenius algebras. The structure theorem for Frobenius algebras may be recasted into an equivalence of categories as indicated in the proposition from this slide. The proof, I give you some element, again some element of the proof, which is not really difficult. By the structure theorem, each radical Frobenius algebra is actually a trivial algebra. That is, it has the zero multiplication, automatically the zero multiplication. There are no other radical algebras than the trivial algebras. Consequently, it is essentially a Hilbert space. So this is the second factor in the equivalence, in the product occurring in the product of the equivalence. Now there is also a direct sum functor for Frobenius algebras, and this functor restricts to the expected equivalence of categories. Another observation about all these structures is as follows. The Frobenius algebras have a kind of Gelfand representation that I now describe. So let me first introduce a category of weighted pointed set. A weighted pointed set is a triple where X is a pointed set with a base point x0, and alpha is a map from the set of all points different from the base point with values in a half-closed interval whose minimum value is a strictly positive constant. So this is a little bit technical, but this has to fit in the picture of Hilbertian Frobenius algebras, and in particular, it has to ensure that a multiplication will be continuous. Morphism between weighted pointed set are as indicated in the slide. So again, these conditions are made to ensure that such morphisms provide a bounded linear map between some Hilbert space. Indeed, we may define a L2 functor from the dual of the category of weighted pointed sets to that of Frobenius algebras. Its value on a given weighted pointed set is a subspace of a usual weighted Hilbert space, which turns to be a semi-simple Frobenius algebra under pointwise multiplication of functions. In the opposite direction, let A equal to h mu be a Frobenius algebra. We can show that each minimal ideal of A is a one-dimensional subspace generated by a unique group-like element. So we may define min of A as a set of all minimal ideals of A, and the weight functions of an ideal as the inverse of the square of the norm of the group-like generator of the ideal. This construction provides a functor. It extends to a functor from the category of Frobenius algebras to the dual of weighted pointed sets. So of course, one has an adjunction between those two categories, and this adjunction restricts to an equivalence of categories as indicated in the slide, whereby semi-simple Frob, I mean the full subcategory of Frobenius algebras spanned by those algebras which are semi-simple. Consequently, the category of Frobenius algebras is equivalent to the product of the dual of weighted sets by Hilbert space. From this, from the previous equivalence, one may deduce other equivalences, and among others, I give you two of them. Finite dimensional Frobenius algebras are equivalent to the product of the category of the dual of the category of finite pointed sets and by the category of finite dimensional Hilbert space. And the category of finite dimensional Frobenius monoids, so this is the index 1 in the second line of equivalence. It means that this is the category of monoids, so semigroup with a unit, is equivalent to the category of finite dimensional Frobenius algebras with morphisms which are restricted to be proper. And this is by the above equivalence, equivalent to the category of finite, to the opposite of the category of finite sets by the category of finite dimensional Hilbert space. So one here recovers a result, again, a result of Bob Koke and his collaborators. My talk is coming to an end, and I thank you for your attention.
Thank you very much for your presentation. So while I wait for some questions to pop up on the chat, I have just a clarification, really. On slide 20, point 2 of your result. So I recall that, well, I may be mistaken, but I seem to recall that there is a similar statement in the Abramsky-Hohen paper, at least for approximate units, so for several Hilbert spaces, because you already have these non-unital Frobenius algebras. So would you mind commenting on what this second point says in addition to what was already stated in that paper? Is it that this extends to every Hilbert space, not just the separable ones?
So you mean that the item 2 is already contained in the paper of
I wouldn't state that with any confidence. I just seem to recall that there is a connection with their result.
What is not difficult to see is that once you have semi-simple special Frobenius algebra, then it is automatically semi-simple, and the group-like elements form an orthonormal basis. So what, if I remember well, what Sanson, Abramsky, and Krisainen states in their paper is that they consider semi-simple special Frobenius algebras, and they have maybe not a bijection, but it is known that group-like elements then form an orthonormal basis, but they were not able to prove that every special Frobenius algebra was semi-simple. So the semi-simple assumption was unnecessary.
I see. So there's it's the one-to-one correspondence statement that's, I see. Okay. Yeah, that clarifies it. It's just my memory is a bit rusty. Sorry. I have Cole Comfort asking whether this equivalence is monoidal, but I am a little bit confused as to which equivalence he's talking about. So I've asked him to clarify.
So probably this one, I think, because okay, I believe this.
The equivalence in your main theorem, he asks whether the equivalence in your main theorem is monoidal.
So this one. I don't know. I did not check this one, but I know that the other one in the last part of my slide are monoidals. So you have to consider here, I don't know, for this proposition in slide 22, I don't know if it is monoidal and for what kind of tensor product, which tensor product I have to consider.
I see.
Yeah, Frobenius algebras are closed by the under the tensor product of Hilbert space, but okay, I did not check if this is a monoidal equivalence.
Okay. I don't see any other questions. So thank you very much for your presentation.
Thank you.